So thank you very much, Molulu. I'm very happy to be here, and I want to thank the invitation to give this talk. So this is going to be an introductory talk about quantum neural networks. So it's a very basic introduction, and I want to explain a little bit what quantum neural networks are. So we were talking about these last talks about supervising learning and machine learning. So this is a little bit different. So first of all, I want to, whoops. So I have, control. So this talk is always dedicated to the memory of Peter Wittek, which was a very brilliant scientist, which was one of the initiators of the field of quantum machine learning. And that he was telling a few years ago in 2018, so that this quantum is going to be not only quantum machine learning, but the whole thing of quantum is going to be really a breakthrough, that it will take 10 years or something like that to be realized. And he was the person, I think, in some ways that initiated the field of quantum machine learning. Unfortunately, he disappeared while climbing on the Himalaya in 2019. But when he was already working in Toronto and had his own company, but he had been previously in Barcelona, and he was a very close friend of us. So let me give you a very brief review of what are these classical neural networks, and then go to the quantum neural networks. So I just want to review what is a neural network and what is the learning capability of a neural network and the storage capacity. And then I want to jump to quantum neural networks to see what is a quantum neural network, in particular attractors, what is the storage capacity, and what we call the Gardner's program and the coherence theory. Okay, so the classical neural network is just the real neurons, no? So this is Santiago Ramon y Cajal, which is the only Nobel Prize in Science that we had in Spain, so we have to put it in all places. It's like that. So it was the one who understood what neurons is, and our brain is just a network of 10 to the 11 neurons, which are, as we all know, cells which they receive, process, and transmit information. And so I want to say that he got a Nobel Prize in more than 100 years ago. And well, it was well known because he was a very rebellious person, all right? So when he was small, he was jumping from one school to another. Nobody wanted him in the school. They considered him that he was a very bad student. And even at the age of 11, he was in jail because he just constructed a cannon and was bombing his neighbor. So, but nevertheless, he becomes a Nobel Prize, no? So when you go to what is a neural network then, so an artificial network, the first model was in already almost 100 years ago, which was a very simple thing to model the brain. Okay, so it was a mathematical function in which you have some inputs that you call it, they are simulating the inputs of the dendrites, and then you have a kind of a step function, and then the neuron fires or not. So it's a binary thing, depending on this step function, which is here. And this was very interesting already, because very soon it was possible to see that with such a simple kind of neuron, which is called this McCulloch-Pitts neuron, already several functions could be, depending on this step function, you could already have a logical table and to simulate the OR function or NOR or NAND function. So people were very, very interested on that. And then immediately after, it started to be this kind of learning. Can we train and learn with these neurons? And the first and most important model of neurons, which is still artificial neurons, which we are still using the same, okay, which is a modification, it's the perceptron, which is the simplest neural network, okay, which you have here 4 things. You have different inputs, and now you have weights, so it's not enough to have inputs. Each input goes with a weight, and then you have, again, a sigmoidal function. So you sum all these things, and you have a threshold, and with that, you have an output. And this is the building block of neural networks, and I have to say that it's of all neural networks, including the quantum neural networks. So, but the development of neural networks was stopped. So this show immediately that you can make any linear separation, okay? So you can, if you have a data and you have a linear plane between this data, you can, with the perceptron, use to classify different data, but of course it was not working for nonlinear data. And well, this kind of perceptron, we can understand it as an algorithm, okay, for supervised learning or an binary classifier. So it was a very powerful thing, but unfortunately now we think that in the a little bit later, at the beginning of the 80s, it was these two physicists, well, computer science, Minsky and Popper, that they decided that that was not good enough because this perceptron could not be used to calculate the Shor gate, so which is addition modulo 2 and very necessarily for computing. So they decided that they kill the field of neural networks for almost 20 years until game industry showed that neural networks are very important and everybody came back. Okay, so there is this deep learning, which is nowadays what it's strongly used, which nobody understands properly how it works, but it's a collection of neural networks with different layers that it has forward and backward propagation, and they are very important. So we know that they work, although nobody knows very well why. And then a little bit of a classification, what is this thing? So you have the deep learning, and then there is machine learning, which is this kind of the science of getting the computers to work without the need to be explicitly programmed by us, and artificial intelligence, which holds all these things. So on all these kind of neural networks, there was one which was very important for physical reasons, and this is the one that I wanted to talk, which is this attractor neural networks, which is a network that evolves on time, okay? And after the time, you have an input, and this input goes to a pattern, okay? And this pattern will be a fixed pattern, and therefore, this was used for associative memory. So I have an input, and I will run my attractor network, and then it will go to a pattern, which will be will be as a memory, will be the closest to the pattern that I have, which is closest to the input. So if I have two different inputs that they go to the same pattern, then these two different inputs are associated to the same object. Yeah? And so it works like that. So you have the way that I will explain it a little bit more. How it works is you have an energy landscape, and then you have some minimum of this energy landscape, and these minimums are the attractors of the patterns. And after some time, the network originally, so the neural network, goes to one of these attractors that they have a basing of attraction. And among all these attractor neural networks, maybe the most famous one was the Hopfield model, which was in the 80s, before this was the killing of the neural networks, in which is very simple. So, well, it's very simple. It's quite complex, but imagine that you have 4 neurons, which are here denoted A, B, C, D, and they are all interacting with all pairwise with couplings that can be positive, +1, or negative, -1. And when you study this kind, so these are Ising model, is an Ising model where you have classical Ising spins, so spins going +, -1. You construct this Hamiltonian, which is interaction, two body interactions between all possible spins, with a coupling Ji equal to Jji, so it has to be symmetric. And the only thing is that the interactions are random, okay? And they can be positive and negative. Well, this statistically, it's a very complex model, which is called a glass. And so one has to put a learning here, and the learning was to update the configuration of the spins in such a way that you reach one of the minima of the energy. And the stationary states will be the states of the minimal energy. And there are many states because it's very difficult. So even to find which is the lowest state. So if you start from a configuration which is close, and I will say what that means, close to one of the configurations of a minima of energy, the network will bring you to there. Okay. So, and this is a dynamical thing. So the learning that you have to put it's just that you have to change every time, which is the configuration of the spins. So you have n spins, okay? You have two body interactions, Si, Sj, and at every step of time, you change the configuration of the spins in such a way that you go to a minimum. So these were the attractor neural networks. And then you can say, well, the neural network, because it has this associative memory, will be better the most number or the maximal number of patterns of attraction it has. So which are the patterns which are the corresponding to the minimal. And in some models, you can look that, well, it can be as maximum, okay? The memories or the patterns or the stationary states of the neural network, which are these denoted by this C mu, okay, which are spin configurations, will be linear with the number of neurons that we have. Okay, so just we can go here. And so this is the storage capacity. So obviously, we would like to have a neural network which has a maximal storage capacity because it will be classifying many different states, okay? But it's easy to see that the storage capacity in these simple neural networks must be as maximum linear with the number of spins that we have. This P equal to alpha n with alpha smaller than 1. So with these things now one say, well, how one goes from a classical neural network to a quantum neural network. And this has some kind of problems. So one can see that if you have a deep learning, so you have this kind of things in which you have an input state, then you have many hidden layers of neurons and then an output state, you can try to model that with a quantum circuit. But there is some things which are a little bit problematic because so we expect that quantum neural networks, what you will do is add quantum futures. So for instance, instead of having Ising spins, you will have qubits, and then you will use correlations and superpositions to the model of neural networks. But this is a little bit problematic because these deep learning or classical neural networks, first of all, are clearly nonlinear, and on top of that, they have dissipation, while a quantum circuit, how we know, or the quantum evolution, it's unitary and linear, and if you want to put dissipation, you have to put measurements. Nevertheless, there is a kind of desiderata of what a quantum neural network should be in this way, okay? So, and it should be able to produce an output state which is the closest possible to the input state in terms of some distance. It has to have computing mechanisms as training rules, so attractor dynamics. And the evolution of the quantum neural network has to be based on quantum effects. And this desiderata was put forward a few years ago by the group of Francesco Petruccioni, which was talking here a couple of days ago. So the first attempts to do that was very old already. So 30 years ago, Maciek Levenstein tried to learn what was the storage capacity and use a Gartner program, but it was a failed case. So it was not possible to get really which is the real storage capacity of a neural network. And then a little bit later, it was a quantum search algorithm, which was very complicated, which shows that for a very particular case, the storage capacity of a quantum neural network can be exponential instead of being linear with a number of neurons. And in 2018, so 4 years ago, there was an example given using also a quantum phase amplitude algorithm by the group of Seth Lloyd, in which they kind of generalize this quantum Hopfield model. And they saw that also you can have, in this case, an exponential capacity. So what we were trying to do is to see how do you can define the storage capacity in general of a quantum neural network, this kind of attractor neural network. So this is a collaboration with people from different people from the group, Maciek Levenstein in IGFO with his people, and I was in the Autonoma with my people. And so we put the quantum information approach here, and we say, well, how one should consider a attractor quantum neural network? Well, this has to be a dynamical process, and we know that any physical process has to be characterized by a completely positive trace-preserving map. So I have a state rho, and I apply my trace-preserving completely positive map, and I get another state, and I know that this map has to be positive. So it has to transform states, quantum states into quantum states. It has to be completely positive. So if I take a state, or if I combine my map with the identity in a superspace, has to give me a state, and finally has to be trace preserving because probabilities has to be preserved. So under this condition, the question of the storage capacity of a quantum neural network can be framed like that. So what is the maximal number that of stationary states that a non-trivial map can have? And by non-trivial, I mean that the map cannot be the identity or a unitary map. Okay? So this will give us the number of attractors. So one can work that and show that there exist non-trivial maps that they fulfill that when applying over a set of linearly independent states, they give this set of independent linear states. And these maps are not the identity. And this is the maximal number of stationary states that a map can have. Okay. So, and of course, if we have n qubits, the number, the dimension of the Hilbert space is 2 to the n. So therefore, attractor quantum neural networks have always, you can construct many different models in which you will have. So all these maps will give you a storage or a memory which is exponential on the number of qubits. So how are these maps? Well, these maps, you can work about these maps, and once you learn how they are and you prove these are the maps, what are quite simple maps, which are easy to understand, which is a map that leaves my states, which are, so for any input state rho, that the map will leave the diagonal elements and it will kill the coherences. So this factor here that you see 1 plus alpha mu nu has to be in such a way that it's a smaller one in the modulus because the map has to be positive. So this is in general, when you have n dimension n, it's difficult to check that the state, the map is positive, but there is a set of conditions, so you use Sylvester method, and you can see that these conditions can be fulfilled. So this is a map which works like that. So if I have my initial matrix, I will have that each element which is in the coherences is reduced by a factor 1 plus alpha mu nu. And this alpha mu nu has to be modulus square smaller than 1. So the action of these maps, it's the following. So if I start in my Hilbert space, which is this blue dot, and I apply the map, what I'm doing is every time I'm reducing the coherences, and after applying my map a finite number of times, which it can be very big, this we don't care, I will end up by the stationary state of the map. And each initial state will finish in a stationary state which is closest to the initial state, okay? So we can think it in another way. So I start by a state which has some coherence, which is my input state. And now I apply my map several times until I end in a state which has 0 coherence. And this is the basing of attraction. And this is the pattern that I will arrive. And there are different patterns, 2 to the n patterns. So any initial state, whatever I put, will end up in one of these patterns according to some distance. And this is irrelevant, so I don't want to go to that. And so according to some distance, I will say which is the distance. So the thing which is relevant here is that while a classical attractor neural network which has n bits can store n patterns or anything of the order of n patterns, a quantum neural network with n qubits can store 2 to the n patterns. So they have exponential storage capacity. So the second question that one has to do is, well, how many times do I have to apply this map until I reach a pattern? Well, since we have seen that these maps are maps that kill coherence, one can use the theory to coherence and to find very easily which is the depth of the attractor quantum neural network. And also one can see which is the distance that you have to use in order to see which is the pattern that you store. So classically, you have to go to minimize the Hamming distance. Quantum mechanically, you have to minimize the relative entropy. So if I start by an initial state and I run my quantum neural network, attractor quantum neural network, I will end in a pattern which is the closest according to the relative entropy to the input that I started. So I can classify to the n states, which this is quite something. And I want to finish talking about a thing which is very important, which is the Gardner program. So Elizabeth Gardner was a very brilliant physicist, which unfortunately died while she was doing her PhD very young, okay, and which changed completely the field of neural networks and has a lot of importance. And what she was saying is that well, it's not important in really to search how many stationary states a model has, but rather the contrary, okay, to fix stationary state or a pattern and to look how many Hamiltonians have such a state of as a pattern. So if the relative volume of Hamiltonians is large, this is a very good pattern. small, it's not important. So she twisted completely the field of neural networks by asking these questions. So she had very few papers because she died very young, but they are classical papers. So this is the one, maximum storage capacity of a neural network. Then comes the space of interaction in neural networks. And last paper, which Mark Messard, the space of interactions, that Gardner, but this is sorry, a paper that it was written in honor to her. So I am a completely fan of Elizabeth Gardner, but I am not the only one. So I was looking who is having this kind of admiration. And then I end up with this citation of Yasser Rowdy, which I don't know him, but he is in the Calvi Institute of Neurosciences. So I assume that he knows what he's talking, and he has the following. He says the following: I don't have any scientific hero, but there are some people that when I read their work, even if I have read them before, their clarity of thoughts, genius, and skillfulness deeply impressed me. And she was talking about Elizabeth Gardner, and this is something that I completely share because, I mean, her papers are just amazing. Okay, so she wrote it before when she was 30 years old. This is 40 years ago, and still you go there, and it's amazing what she did. So we were trying to do the same for the quantum neural networks. What will be the relevant question here? Well, the relevant question will be that instead of asking how many Hamiltonians they have a given pattern, so we'll have to ask, in the space of completely positive trace-preserving maps, how many of these have maximal storage capacity, okay? And also, we want to ask, maybe we don't need to have maximal storage capacity, so because it's exponential, but maybe it can be very large, but not exponential, much more than linear, that will be also good. So the second question is, say, in the space of all CPTP maps, how many will have a large storage capacity? So we were calculating that, and this is rigorously speaking, okay, one has to do the following calculation. So which is the relative volumes of CPTP maps that when they act in a Hilbert space of n, dimension n, which can be 2 to the n qubits or whatever, have at least m times smaller or equal n stationary states as compared to all possible CPTP maps that they act in this space. Okay, so this is exactly what it means, the relative volume of maps. So if we find that there is only one map in the whole manifold of physical maps, this is irrelevant, so it doesn't have any importance. Okay, but if we find that the relative volume is very large, then that means that these attractor quantum neural networks, they really have physical sense. So to calculate that, it's a technical thing. I don't want to enter to that. It's not relevant, so you have to do some things because the volume of maps is not an Euclidean volume, so it's a little bit different. But this is a calculation that one can do. And so you have to put some conditions, and you will say, well, I want to, of course, you always put thresholds. So you want to know which maps are good up to some threshold. So they have exponentially large, or they have exponential or very large memories up to some threshold, the accuracy of the map. And when you do all these things, you end up with this result. So which is that the relative volume, it's very large, okay? Because it decreases with m, okay? So that means it's, to our surprise, we were expecting that that will be much smaller, that there are infinite many maps that they have an exponential storage memory. But it's not enough that they are infinite, it's also that the relative volume, it's very large. So this is a very useful thing. So I would like to finish here saying that while we have been working on that, these are the papers that we were doing, okay? And that it's very easy to use the theory of coherence to understand attractor quantum neural networks, because what we saw is that these maps, they will always be maps which they are what it's called non-coherence generating, and there is a whole formalism, and you can show how is, well, when it's possible to use superpositions and entanglement to increase the performance of the map and to have memories which you can reach much faster than in normal cases. And with that, I would like to thank you. Finish here. Thank you very much.
I have two short questions. So the first one is, I mean, this dynamics of the Hopfield model that you described looks like annealing, classical annealing, or is slightly different? Because it's something. It's classical annealing, right? All right, right. That is, and the other question was about linearity of in quantum. But if you would monitor and change, then yeah.
The way to put dissipation, absolutely, you're right. It's putting measurements. Okay, so if you monitor and you change, and then you can do it. But even without doing that, so there are here two things. No, there are many things to study. Let's say like that. This is a super preliminary thing because this is like the perceptron of Rosenblatt. But now you can do a second layer quantum mechanically. Okay, so put another map and so on. So this is very, very, very preliminary studies. So it's just putting that. Yeah.
Okay, there's a question in the chat. After training quantum neurons, how can we store them in the presence of eventual entanglement in the network?
In this kind of neural networks, okay, so if the neural network, the quantum neural network attractor, it's perfect. So you have this, sorry, let me put it like that. Okay, let me go back. Okay, so what we were able to show, if you have a map like that, which there is no error, okay? So really, it works like that. Neither coherence or entanglement helps. It doesn't help, okay? There is nothing you can do. But if you assume that your map is not perfect, which is the typical thing that we always assume, which means that, for instance, instead of going always with this weight to the diagonal state, so if you, let's put it, if in this matrix that you have here, you add some errors, okay, both in the diagonal places or in the off-diagonal places, some errors that they have physical sense, okay, which you can put, then you can show, this is a difficult calculation because this is n-dimensional, all right? So this is the case, the toy model in which you have 2 qubits and you can do some things analytically, but when you go to higher dimensions, this is kind of complicated. But in this case, when you put errors which are quite logical, that sometimes, for instance, you miss one of the off-diagonal elements by a factor epsilon or something like that, then depending on the type of error and using coherence theory, you can show that entanglement can help. And what doesn't mean it can help? It means that, so you take an ancilla, like always, okay, and you put your ancilla and you entangle with your initial state. So you take a qubit and you have a physical state, which is, I don't know, imagine 2 qubits, and now you entangle this with one of the qubits with your physical state. And now you run your neural network, and then you will reach the stationary state, well, for some time, and then you discard the ancilla. This is the typical thing to do it. Well, then we know that the neural network maybe has to run much less times, so it's much faster. And this is important, okay? Coherence doesn't help, okay? So if you add an ancilla and you put a superposition of with the ancilla and so on, this doesn't help in any case.
Thank you very much, Professor Anna.